Hello, Chemistry 30, and welcome to your Q&A for April 27th. This is probably going to be a little bit of a long one, so there were quite a few questions on that check-in form that I'm going to be going through. Yeah, again, there's time signatures in the description, so you go ahead and pick what you are interested in. Don't feel like you have to listen to all of it. Maybe this is something you play in the background, and then when it gets to something that you are confused about, then you can watch the video, that sort of thing. But anyways, I think it's important that when you have questions, I give you some answers. And this is kind of our primary mode of you asking questions and then me, being able to answer them outside of the Zoom tutorial sessions. So I think it's a good thing. But anyways, let's get into it. So first of all, I thought I would put in the data from your survey type check-in thing, some questions that were asked, just what you answered, because I think it's interesting for you to see what the rest of the class thinks and give some value to the form itself. So first of all, how did you find the workload this week for Chemistry 30? 80.8% of you felt like it was okay. Then some unknown percentage, few people or one person or something, said that it was not enough, and then 15.4% of you said that it was too much. So I think we're pretty close to the right mix here. I understand that some of you feel like it is too much work. It's tricky with Chem 30 because I want to make sure that you are getting all the information you need going into post-secondary, but I realize that some days, especially last week with the assignment, it can seem like a lot. And that assignment in particular was probably tough for some of you because there was that long break, Easter. Man, that was the longest Easter break I ever had. And I think a lot of that has to do with us being in isolation and just kind of stuck. So time goes by slow. And I know that it's easy to forget over that period of time. So I get it. Last week was maybe a little bit rough, but I think we're pretty close to the right balance for workload in Chem 30. This is interesting. What is the average amount of time you are spending on school stuff? So I'll let you take a look at a graph. Most of you fit into that 5 to 6 hours or 3 to 4 hours. A few people are kind of 20% are actually more than 6 hours. So sounds like maybe in some classes you're getting quite a bit of work that you have to get through, or you're just kind of getting to that higher level, which is good. Maybe you're putting in some extra time, making sure that you really understand the material. Pineapple on pizza. This was controversial. Almost a third, a third, a third. 38.5% of you like it, 26.9%. It's kind of like, it's fine. Doesn't ruin the pizza completely. And then 34.6% of you just absolutely hate pineapple on pizza. I'm probably in that red category of it's not something I would actually get normally on a pizza, but I will still eat the pizza. All right, so let's get into the questions you guys asked. So this was the first one that I kind of thought I should address, and I just went through this not in any particular order, but just in terms of when the check-in form was submitted. So unlike last time where I kind of split it up into academic questions that were about material and then other questions, I just kind of went in order this time. So first of all, if batteries are a collection of cells and cells require electrolytes to function, but not all batteries are full of fluid, how do normal small batteries work? Are they solid electrolytes or maybe gel ones? So the answer is yeah, basically it has to do with paste normally, which means there is some liquid in there, but it is very heavy in the solid content. So it's not free to move around, but there's enough water in there that allows the electrolytes to move back and forth. So I pasted in a picture of an alkaline battery, a normal kind of AA battery, and what would be included in that. So I think it's interesting to maybe point out a few things. So first of all, the fact that we have this anode of powdered zinc, and the powdered actually helps in terms of the surface area in order to get more current going through that. So more surface area is a better thing. So I have powdered zinc that acts as my anode, and then there's actually brass in here that is acting then as my electrode for the anode. So it's actually an electrode that's kind of almost made of two things. I have my powdered zinc, and then I have the brass, which isn't going to corrode as much, right, and react as the powdered zinc would. For the cathode, I have a paste here of manganese dioxide. So that's that, we call it manganese 4 oxide. That's that MnO2 solid that you find on your redox table as a pretty strong oxidizing agent. So that's what's going on there. And then it's in a paste form So that means that you have that MnO2 and then it's mixed with some water and then also some electrolytes in there as well. And then we have carbon, which is actually acting as kind of our more surface area inert electrode. You can see that this then makes contact with the top where I have my steel plated positive cover. So that's for my kind of cathode where it connects, which is making contact to the carbon inert electrode. And then I have my manganese dioxide powder as well. I have my porous non-woven fabric separator here. So this is allowing electrolytes to move through without complete mixing, which is interesting. And then I have kind of packages, and you can see that I actually have this layer at the bottom that makes sure that I'm not having the manganese dioxide mix with the anode material right here. Okay, so that's an alkaline battery, so hopefully that makes sense what's going on in that kind of format. But the answer is, yeah, we don't have liquid for electrolyte, but instead we have, yes, a gel or a paste that the electrolytes can travel through, but it's not liquid sloshing around. Now, if you take a look at a car battery, that actually has liquid sloshing around. We have sulfuric acid in there. There's my daughter sneaking past me. Sulfuric acid in there, that is the electrolyte as well as being involved in the reaction for a car battery. So we actually have electrolyte liquid going on there. Let me pause this, talk to my daughter, and I'll be back. My daughter was informing me that she doesn't want to do her homework, which she asked for because she wants to do homework while my son did his work. So I gave her a color by numbers and she decided it was too much work. Okay, so moving forward, let's move on to the next question. So somebody's saying the thing that messes them up is going through the redox table and trying to find the right thing and mixing the strong or missing the strongest OA or the strongest RA. One thing that can help with this is putting in some markers in your table and just doing some highlighting, just so you have some visual markers for you as you're going through it. It makes it easier. So I would suggest that you do some highlighting of a few half reactions, and then it will just help your brain kind of know where some of the OAs and the RAs are. It just helps. So if you want to highlight the water half reactions here, and then I have another water half reaction here, and then I would also highlight the hydrogen half cell here. So if you take a highlighter, you just go across here, here, and here, then it gives your brain just kind of some visual things to look at as it's going through the list, which will make it easier for you to find the SOA and the SRA. It won't be maybe a conscious thing, but it helps your brain map reactions that it's seen by seeing the relative position of it as you're going through. So it's probably something that we should have done earlier in these two chapters, but maybe now it's something that you can do that will help you see where different half reactions and OAs and RAs are. So I'll encourage you to take a highlighter and highlight this row, the hydrogen row, and then the next water row, and then that splits it up into fourths, right, of kind of like a quarter, a quarter, a quarter, a quarter, where you can see where half reactions are in OAs and RAs, which may help with that problem. All right, nothing in this new unit. I'm understanding it well for the assignment. I think it would have been better if we would have done it before the week off. It was harder after the break. Yeah, probably would have been easier to get it done. I was kind of at this line of thinking like, oh, I could maybe squeeze it in, but it would be really high in terms of workload. So then I also thought that it would be nice for you to have something when you got back that forced you to refresh before we moved on to chapter 14, because it is still continuing the unit. So it was a bit of a conscious decision that had to do both with how much I could fit in before the break without overloading students, and then also with kind of having an advantage of having an assignment where you had to go back and make sure that you understood material for going forward. My focus is on you guys making sure that you have good learning, right? So would marks maybe have been higher if we did it before the break? Yeah, maybe, but I think that it's better for learning, which is kind of our new focus, is mainly about learning, to do it after the break, to have a refresher before moving on to the next chapters. You're going to actually figure out pretty soon here how marks and stuff are going to look going forward. There's going to be some announcements and stuff coming out really soon from the district. So this again kind of reinforces that we need to focus more on the learning than we need to focus on getting good marks on stuff, as we're going to find out in a bit. Okay, so it was more of a learning decision than a strong performance from students decision, and I felt that it was better for the learning going forward into chapter 14 for you to do that assignment after the break. And also, like I said, it would have been really tough to fit it in for time for students without it being overwhelming that week before the break for workload. All right, next question. I am still confused about oxidation numbers. I think I know how to write them, but I don't understand what they are. Yeah, it's a theoretical concept. It's not that the electrons are actually necessarily in a place, but we're attributing where electrons are. So let me just give you an example and then talk about what it means. And we'll just pick a really simple example of water. When I take a look at water and I assign oxidation numbers, I say that oxygen is -2 and hydrogen is +1. So what does this mean? This means that oxygen, when it's in water, has 2 electrons that we're giving it. We're saying it belongs to oxygen that it didn't have before as an atom. When I talk about atom or elements, it has an oxidation number of 0. It has the electrons that it came with, and that's it. But when we have oxygen in water, we say that it actually has 2 more electrons that it came with, and that's because it stole electrons from hydrogen. So we're saying that those electrons belong to oxygen. Hydrogen, we say that it lost its electrons. It has 1 less for each hydrogen than it had before as an atom, which is why we say that hydrogen has the oxidation number of +1. So what it is it's electron bookkeeping. It's keeping track of where the electrons are. And we're saying that electrons are right now 2 of them with oxygen that it didn't have before as an atom, and hydrogen each has 1 less than it had as an atom before it was in this compound. So it's keeping track of where the electrons are. Okay, and by keeping track of where the electrons are within a compound, then we can figure out what happened with oxidation and reduction, because we can see when a transfer took place by looking at the change of oxidation numbers and where electrons essentially are. Now, this is oversimplification, because we know that in water, it's a covalent bond. It's a polar covalent bond where electrons are spending more time with oxygen than with hydrogen, but the electrons are being shared, unequally, but shared. So we are saying that those electrons, because they are more with O than with H, that they're with O, and we're giving it a number of -2. And in the same way, we're saying that electrons are not as much with hydrogen. Okay, so we're giving it a +1. So what we're doing is we're tracking where electrons are by giving them to one atom and saying this is who they belong to right now, and they don't belong to the other atom. I'm choking on my own spit. All right, so that's oxidation numbers. It's electron bookkeeping. We're trying to figure out where the electrons mostly are, which atoms they're mostly with within a compound. In a voltaic cell, the anode is always in the left porous cup and the cathode in the right porous cup, or it doesn't matter as long as the electrons and ions are moving in the correct direction. That's completely right. It doesn't matter. We're often just doing anode on the left and cathode on the right because we were looking at cell notation, and that is how the cell notation is. We have anode, electrolyte, porous boundary, electrolyte, and then cathode. So because we have that normal format, then we kind of follow that going down to the diagram, and we do anode on the left and cathode on the right. But you could be a rebel and mix it up. You could put the anode on the right, the cathode on the left, and that would be completely accurate, which is why we label the anode and the cathode on the diagram. So number 6 in the work booklet is one that was asked about in this question of kind of like, in this example, could we put the anode and the cathode anywhere? And yes, we can. In fact, let's right now say, hey, we're going to put the anode right here, and we're going to put the cathode right over here. Okay, we're going to right away mix it up for anode and cathode. And this doesn't specify, because it's not cell notation, doesn't specify what we have in terms of anode and cathode. So we have to figure out what our, that fun little thing again that it does. We have to figure out what our OA and our RA is and kind of go from there. So I have tin metal, I have zinc metal, Zn solid, I have tin 2 sulfate, SN2 positive aqueous, I have sulfate solution, SO4 2 minus aqueous, and then I have sodium ion, and I have chloride ion, and then of course I have water. So what I would want to do is I would want to figure out my OA and my RA based on this. So I got zinc going on, I got tin going on. I know that those are going to be my two electrolytes. So I'm probably kind of looking for a zinc tin cell going on. So here's my zinc. Okay, it's my strongest RA. And then I have tin, which I go from the top left and go down. And it's right here. So that's my strongest OA that I have. I don't think I have anything better. I've got that sulfate reaction somewhere up here, but I don't have the hydrogen ion that it needs to go with it for this. So I don't actually have that going on. So it is the tin 2 as my SOA. And then I have the zinc as my SRA. All right, so my zinc is going to be my anode. So this is Zn solid. My anode is, of course, negative, and then my cathode will be positive, and that's going to be the solid tin, Sn solid. Okay, so this is where I'm going to have my tin 2 positive aqueous and my sulfate electrolyte, because what's happening at the cathode is I have my reduction taking place of Sn2 positive aqueous plus 2 electrons gives me tin, Sn solid. And then for my oxidation half reaction, that Zn solid turns to Zn2 positive aqueous and 2 electrons. That's my oxidation. Which means that my net is Zn solid plus Sn2 positive aqueous gives me Zn2 positive aqueous and Sn solid. It's 2 and 2 electrons, so it just works out. I can combine it, and that's my net reaction. So this electrolyte, the only electrolyte that I have left to use, is my sodium chloride solution, Na positive aqueous and Cl minus aqueous is over here. I don't know what's in this salt bridge. I can just make something up and say it's something like sodium sulfate. Sodium sulfate, always a good choice for the salt bridge. Okay, so what's happening at the cathode, just to kind of spell out what's taking place, is I have Sn2 positive aqueous, which is coming to the, migrating towards the cathode. It's meeting up with 2 electrons, and then I have plating on here my Sn solid, so it's building up tin. So my cathode is growing as time goes on. Well, my anode will, oh, that was horrible. My anode will be shrinking, right? What's happening is this is getting smaller as time goes on. And the reason why is the zinc is forming Zn2 positive aqueous by releasing 2 electrons. That's my Zn solid that's doing that. I know, too small to read here. And then I have electrons going from anode to cathode. I have migration of cations towards the cathode, and I have migration of anions towards the anode. So for anions, I got sulfate migrating towards here as well as chloride, right? And then for cations, I have sodium ions and tin 2 ions that are migrating towards the cathode. So they're moving to the left. So yeah, we can put anode on the right, cathode on the left. The only reason why we have been doing anode on the left and cathode on the right is simply because that matches the cell notation that most questions have been presented with. So that's what's going on there. It's no like set way that you have to do it, but that's just how it's been done because of the setup. And in fact, I think in all the keys and stuff, I've always done anode on the left and cathode on the right. So this answer I have written here doesn't match the key that I have set up. It's still right, but I've just flipped the anode and the cathode. Okay, how long should a voltaic cell question realistically take? I feel like I'm using a bunch of time for one question. I feel like, you know, for a student newly doing it, it's going to probably take about 20 minutes per question. And then as you get better, it's probably going to get down to around 10 minutes per question. They take a lot of time. They do, which is why when I gave that assignment for voltaic cells, we started out by just doing 3 or 4 questions and then left the other 2 for afterwards because it's a pretty mammoth thing to get through all those questions. They take a bit of time. So I guess my simple question would be somewhere between 10 and 20 minutes, depending on how many you've done. All right. Do you have to remember oxidation numbers such as oxygen is usually -2? Yes, you do. You should know that oxygen is -2 if it's in a compound, -1 if it's in a peroxide. You should know that hydrogen is normally +1 unless it's in a metal hydride, in which case it's -1. And then also, when you have an ionic compound, you split it up into its 2 ions. and then the ions that are in the ionic compound will have their charge. Besides that, of course, elements are zero, right? And ions have the charge that they have. So you should memorize those rules for oxidation numbers. They're incredibly important. Almost all the time, though, what we're doing is this: oxygen -2, hydrogen +1, and then we figure out the rest of the oxidation numbers from there. And that big thing of splitting up ionic compounds into their two ions in order to figure out oxidation numbers from there. Labeling diagram still hasn't really caught on for me. Could you do more examples with different diagrams? Yeah, and this is the last question, by the way. This is the end, I think, that I've got here. Nope, almost the end. So let's tackle a weird diagram. I just kind of actually looked up, hey, voltaic cell diagrams on Google Images, and then just kind of grabbed one to work out and then picked a random cell so we could work through something that was very not descriptive, not a lot of scaffolding, so we could analyze the cell and go through it. Because of the kind of space constraints, I'm probably not going to label as much, especially in the porous cup here, as I normally would. But we'll do the minimum of like what we would normally do for a question, what the expectation would be for a quiz or a test. So magnesium aluminum cell and label everything. So I've got, if I take a look at magnesium and aluminum half reactions, I have aluminum right here. Oh, and magnesium is right here. So aluminum will actually be my SOA, and magnesium, this is a horrible example, and I'm not redoing this video. So let's just change this out for something else. Can I explain why it's a horrible example? It's a horrible example because of the fact that my SOA is below water if I'm doing an aluminum cell, which doesn't work. Okay, so we're going to pick something that's a little bit higher up. So why don't we change this instead to an iron magnesium cell? And we're going to use iron 2 solution for it. So magnesium iron cell, and we'll say iron 2 here just to be really specific and label everything. So why don't we switch it up again and put anode on the right just for kicks. We could have picked any direction, it doesn't matter, but let's make this the magnesium, okay, Mg solid, which is going to be my anode. And anodes are, of course, negative in voltaic cells. And then here I have my iron. Let's do this as Fe solid, keep it consistent. Fe solid, which is my cathode, and it has a positive charge. So I know that electrons are going from my anode to my cathode, right? So they're going in this direction. My cathode is going to grow over time because I'm going to have iron 2 meeting up with the electrons, and then from there setting up as iron on the outside. So let's make this FeSO4 aqueous. I'm just going to pick the sulfate ion because normally it's quite inert and good to use in cells. And then why do we make this magnesium sulfate right here, MgSO4 aqueous, right there. Okay, so that's what's going to be an electrolyte in this side, this half cell. I'm now curious and hoping that these are not solids for solubility, and it worries me enough that I'm just right now going to check. I wish I knew my solubility table better than I do. We're all good. It's all fine. Okay, so now that I've got that going on, I'm all set up. I'm going to have ions moving through my porous boundary, going back and forth. So I'm going to have anions moving from the cathode to the anode, right? It's going to migrate towards the anode. So this is my anions. And then I have my cations moving from the anode to the cathode, migrating towards the cathode. Specifically for anions, it would be sulfate moving through here. That's the only anion I have. And then for cations, it would actually be the magnesium that I end up having, Mg2 positive, that would be migrating through this porous boundary towards this. So that's what would be going from the porous cup, the inside, to the outside. All right, now what would also be interesting maybe for this cell is figuring out what the voltage would be. So for my cathode, I have negative 0.45 volts for my iron half cell. And then for my magnesium, it's negative 2.37 volts, so minus 2.37 volts. And that would get me a positive 1.92. Positive 1.92 volts is what I would get for a voltage for this cell. So that's what it should read for the voltage if I look to the voltmeter at the end of the day. Okay, so that is another example. Hopefully that helps. All I'm doing is I just kind of figure out my OA and my RA, right? So I figured out, once I figured out that my initial choice was not good for a cell, that iron 2 was my SOA and magnesium was my SRA. And then that tells me that my cathode, right, where my reduction will take place for my strongest oxidizing agent, will be iron, or really any electrode. It could have been something inert as well. As long as it conducts, it's going to get plated. And then my anode would be magnesium. Now, this is kind of another point, is that I could use any metal at all. No, I want to change that. For electrolytic, it's true. As long as it's something that's inert or doesn't react, doesn't matter what I use for the cathode, it could hang out here and be fine and would get plated. So for example, you could have something like a carbon electrode. You could put it in there and that carbon electrode would get plated with iron as the reaction takes place, which is kind of neat. All right, last question. When stating the electrolyte, should we separate it into major entities like Na positive aqueous, Cl minus aqueous, or just leave it as NaCl aqueous? Doesn't matter, your choice. It's equivalent when we're listing the electrolytes. We're not showing the action of that electrolyte and what it's doing. We're just saying what we have in there. So either option is fine. This is the easier option, right? To write it out as a compound, but writing it out as ions is great. Okay, so either or, doesn't matter. That's it for today. That's the Q&A. So yeah, hopefully you got some value out of that and have a good rest of your day.